So, do students join this meeting, or is it mostly INAE members only?
Pardon? I couldn't get you.
No, do students join this presentation, or it's only for INAE members?
No, not many students will be there because only actually this faculty, fellows, and some researchers actually they will be joining.
Okay.
Then, because with the student, the problem is actually what they are doing nowadays. So they are when you are speaking something, or all these your screens, etc., they will share it, and immediately they will pass on to others. It creates a lot of problem. Once or twice we face this problem. So, of course, your lecture will be recorded, and if you permit only, then it will be circulated to others. If there is any confidential information you don't want to share, please feel so. Actually, will not share. Okay.
Yeah. So far there is nothing. Yeah.
Okay. Okay. Definitely. Then we'll do so. During your time, Baleswar was actually one of the JEE center.
Not during my time. Not during my time. During when I was a student, Balasar was not a center.
Yes, I remember actually it used to be a center long time back.
No, maybe. But see, I had to go to Cuttack to do the exam.
Okay, fine. So maybe I'm confused. No, it was earlier there.
Yeah, but in my time, the closest.
So it was not there. Okay.
Yes, center
so maybe
was
up to 80s or so. Balasore was actually one center, I remember. 80, 85, 82. Okay.
Okay.
So actually now we'll start. Very hearty welcome to all who have joined to this 76th distinguished lecture, 75th distinguished lecture, which is being given by none other than Professor Sunita Sarogi of IIT Bombay. So, Professor Sunita Sarogi is a graduate of IIT Kharagpur, and after his graduation, she moved to US for her further studies and did her PhD from University of California, Berkeley, and also her husband, who gave our 74th lecture, okay, Professor Somen Chakrabarti, he also joined them UC Berkeley, and both of them actually they did their PhD, and later on both of them joined IIT Bombay as professor, as a faculty in computer science department. Professor Sunita Sarogi researches in the field of database, machine learning, and applied NLP. She is institute chair professor in the computer science department and was the founding head of the Center for AI at IIT Bombay. She got her PhD in database from University of California at Berkeley and bachelor's degree from IIT Kharagpur. She was also worked at the Google Research, CMU, IBM, Alumden, Research Center. She is an SCM fellow and was awarded Infosys Prize in 2019 for engineering and computer science, and the distinguished alumnus of IIT Kharagpur. She has several publications, including notable papers awards in SCM, SIGMOD, ICDM, and NeoRIPS conferences. So far as her abstract of our lecture is concerned, it is already circulated. You must be actually, you must have seen it. So before actually, now actually I will request Professor Sunita Sarogi to please make our presentation, and it will be followed by question and answer and vote of thanks. Professor Sunita, please go ahead. Okay.
Okay. Thank you, Professor Acharya. I will share my screen first. Okay. I hope you can see my screen.
Yes, absolutely. Okay.
Right. Yeah.
No issue.
So large language models, or LLMs, like ChatGPT or Gemini, they have dazzled the entire world by their intelligence. And one particularly impressive aspect of their intelligence is the ease with which they can adapt or learn new tasks based on just a few examples of input-output pairs in the context or the prompt. This capability is called in-context learning, and it is celebrated as a major breakthrough that emerged just after doing simple next token prediction loss-based training of the large language model. In this talk, I will show that while in-context learning works for certain classes of common tasks, for more structured compositional tasks, in-context learning is poorly understood and has certain limitations. And then I will present some ideas on what one can do around those limitations. This has been a work which I have done for almost 3-4 years now, and with several of my students and other faculty collaborators who are mentioned here. So before we go into LLMs, I just want to abstractly define the adaptation task. What do I mean by adaptation of a model with examples? So this particular operation is also called few-shot adaptation. So here, let's say you have a trained model, would be an LLM, which has been trained on huge amounts of data, and not just huge amounts of data, the data is also very diverse. So a toy representation of a large diverse data set is in this diagram, where you can think of the color as denoting diversity. And largeness I'm not able to show here, but it's just showing that normally in machine learning, we assume that data is independently identically distributed, but that is not the case for this large scale training that the LLMs undergo. So we have to assume that the data has huge diversity, and this model is trained on this diverse data set, and that model we are calling M theta. But no matter how large or diverse your training data is, when a model is used by millions of people all around the world, there will always be new tasks which the model will not know how to tackle. And that is what raises the need for adaptation. And for adaptation, you can perhaps even give the description of your task in natural language, but there are some tasks like, say, translation, for which you cannot just describe your task at a top level. One of the most effective ways to describe a task is to just give examples. So let's assume that this capital T here denotes some examples of input output pairs. So when the input is X1, the output will be Y1, input is X2, output will be Y2. So the user gives K such examples. And now during model adaptation, our goal is to find the best blend of the pre-trained model M theta with this training data, the few short examples T. And the model adaptation process will take these two inputs and output a model which we call the adapted model, which will behave in the way that if you have more new unseen examples which follow the same distribution as the distribution from which these few short examples are sampled, then the model will give predictions which are more accurate than if you just used the base model. There are several examples of model adaptation in real life. So suppose if you have trained a model for conversation assistance on a large number of users, every new user might have his or her own style, and it might be useful to adapt the model to the new user's style. One domain where I have spent some time in the adaptation task is when you are trying to generate code to convert natural language instructions to access information from a database system. And that code language, say if it is SQL, then a model is typically trained with text to SQL pairs from several database types. But then there might be, each company might have their own private database, like say there might be a private pharma database on which you want to pose your natural language question, and it's important then to adapt the pre-trained model to new database schema. Another example, of course, is adapting to languages, a low resource language. So suppose if you have trained an LLM for a large number of diverse languages of the world, but there will always be languages for which the LLM may not have seen enough training data, and it is important to be able to teach the model new languages. Now, model adaptation is very challenging. First, from the accuracy viewpoint, because in order to get good accuracy, you need to delicately balance the information which is there in the small but highly relevant few short examples, which are the training examples relevant to the task T, and the large model of mixed relevance. If you adapt too much, you might overfit, and if you adapt too little, there might be no change. And the second desiderata we might have is that of robustness. We want the model to not be subject to brittleness and exhibit very widely different performance based on the specific set of examples which were used for adaptation. So that is another thing to worry about, to create a robust model. And finally, we want the adaptation process to be efficient. The time to adaptation should be small. Ideally, we want the adaptation to be on the fly, which is called online adaptation. And also, during test time, for every example on which we want the model, the adapted model, to produce an output, that running time should not increase too much. So this topic of model adaptation is not a new topic. It has been around for almost 30 years, and several varieties of tricks have been proposed. So crudely, the set of methods I would categorize into 4 types. One of the most prominent methods for adaptation is fine-tuning. Excuse me, I just wanted to say that there is an echo coming from somebody's connection. Maybe if everybody can mute if they are not talking right now. Of course, I welcome people to unmute and ask questions, but right now I'm getting an echo from somebody's connection. So could I request everyone who is not wanting to say something right now to please mute? There is a lot of echo coming from somebody's connection.
Please actually switch off your mobile. This might be creating problem. Okay, please go ahead. Now I think everything will go all right.
Okay. Right. So the model adaptation methods, one is, fine tuning, which is the most popular method for adaptation. Second is a mixture of experts, adaptation with task vectors, and adaptation using matching based methods. So these are conventional methods. And for each of these methods, there has been deliberate plan to make the adaptation process accurate, efficient, and robust, either by designing specific interventions during the training of the original model itself or at the time of adaptation. To just show an example of such an intervention, suppose when you fine tune a model on a limited amount of data T, then you are actually changing the parameters of the model so as to minimize the error on the few short examples. But so this is the point to remember, that matching is a very delicate task, and there is a long history of methods which have been proposed for adaptation, and they all tried to carefully change either the way the model was trained or what was done during adaptation to make the model adapted to the new task. With this as the background, now we bring in large language models. So large language models have been trained with the next token prediction laws, and they have been trained on huge amounts of naturally occurring document collections. And a surprising finding was made in this very famous paper, which appeared in NeurIPS 2020, that a model which has been trained with just next token prediction laws on huge natural document collections is able to learn new tasks just with the examples of the task provided in the input of the model. So here is an example. Suppose your now model M theta is a large language model like say Gemini or ChatGPT. And as an input to the model, you give your examples of input output pairs. You just concatenate them one after the other, and you just give them the input followed by your test example. And what was surprisingly found was that the model is able to online teach itself the task based on the examples and produce an output for this X test, which mimics that of a model which has been adapted explicitly, like as if you have fine-tuned on these examples, on these new test examples. And this was very, very surprising. So here is an example of the capability of few short adaptation that you can see with LLMs. Suppose to an LLM, you give this sequence of numbers. There is no explicit mention of which is the input, which is the output, and the delimiters can also change from example to example. You give this series of numbers and you ask the model to generate the output. Surprising, the model is able to identify that here you are actually trying to do multiplication and it outputs the correct answer. So you can see by changing the test example, and it really does seem like it has learned the multiplication task. So for people who have been doing machine learning and training models, this came as a big surprise, and there has been a lot of hypotheses proposed on why does in context learning capability emerge in these transformers, which are the basic models underlying large language models. are trained with next token prediction loss. And many hypotheses have been proposed. So the first hypothesis claims that transformers implement the gradient descent algorithms over in context examples. A second hypothesis claims that in context examples recognize tasks in pre-training. They do not really actually learn the task exhaustively. They just have, because they have seen such huge diverse collection of tasks in their training mix, the in context examples just help it recognize the task and then just recall the answer from, or recall the computation path from its training set. A third hypothesis claims that the self-attention operation, which is something which is at the core of the transformers, actually is able to implement some kind of a associative recall, which at least helps it do in context learning for discrete tasks. So, so we will not go into details of these hypotheses. Just this one hypothesis I will talk about, which is about the transformers implementing associative recall. So what people find is that large language models can learn new input-output mappings, which could not have been in its training mix. And to explain that, there is this third hypothesis, which says that the self-attention implements matching-based adaptation. So here is an example of the way in which the transformer architecture might be able to implement this matching-based adaptation. Suppose you give to a transformer this sequence of 5 tokens. Hello followed by the number 11, goodbye followed by the number 77, and then the word hello again, right? And you will find surprisingly that the LLM is able to identify that, okay, when I put hello here, the number 11 should be output. So the way it is able to do it via self-attention logic is explained via this diagram. So the first layer, it implements, so what this hypothesis claims, that the first layer, it implements the via attention, it learns to copy over the word in the previous position as a key. And the second layer, it matches the last test X with the stored key and outputs the value which is at that position. And that's how you're able to get the extra. So this kind of an explanation of the roles of the two layers of the transformer is not very surprising, but there is this subsequent question which was asked by other researchers about why should a transformer orient itself to create in context induction heads while it is being trained with the next token loss. Okay. So this question was answered by this paper, which shows that in naturally occurring data, there are enough repetitions, and the transformer finds that the induction heads, if they form, then it is able to harness the repetitions to better learn. And that is how induction heads get formed. I'll skip the details here, but this is a very interesting paper which explains why the transformer is able to learn totally new tasks without any explicit attempt for teaching it to learn new tasks. So although this theory of induction circuits is very neat, subsequently, we have been looking at this problem, as I mentioned, over the last 2 to 3 years. And we found that while this hypothesis is able to explain why in context learning happens for classification and regression, it cannot explain for many other structured output tasks, for example, code generation or translation, why in context learning should work. So in this remaining part of the talk, I will evaluate in context learning on structured sequence to sequence tasks. If there are any questions on the part so far, I will be happy to take right now. Otherwise, I'll go to the next part. Okay.
Am I audible? Am I audible?
Question and
madam?
answer could be?
Yes, yes.
Yes, yes.
Oh, okay. The professor is saying I can wait till the end. Okay. Question and answer I will ask at the end, as he is saying. Okay. You please proceed. I will ask at the end.
Okay. Okay. Yeah. So what we are now evaluating is the in-context capability of these sequence-to-sequence learning tasks, which are more complicated than simple scalar classification. And I'm calling these as structured tasks for the reasons that I will go over next. So here, let's assume that we are given as input X a sequence of M tokens, and we need to learn to produce as output Y a variable length sequence of say T tokens, but T could vary from sequence to sequence. And I'm calling it structured because the dependency of the Y sequence on the X sequence can be decomposed in terms of simpler structural units. So there are several real life applications which do not have enough training data, so that even a large language model may not know how to perform tasks in this setting, where such few shot adaptation becomes very important. For example, if you're trying to do code generation for a new language, like semantic parsing for custom APIs or languages, or translation from or to extremely rare languages, or text to SQL for new private enterprise schema. So when we talk about in-context learning on sequence-to-sequence tasks, to the LLM, we want to feed as input K examples of sequences. So this X1 to XM, this is for the first sequence, the input of the first sequence and what we expect as output of the first sequence, and so on and so forth. We provide like this K such sequences concatenated. And now for a new sequence of length M, our goal is to predict the output Y sequence token by token. And this task is structured because the true label Y1 to Yn has to be composed out of subparts of multiple in-context examples, and no single example is wholly relevant. And the irrelevant parts of other in-context examples could interfere. So in order to evaluate the in-context learning capabilities on sequence-to-sequence tasks, we decided to test on synthetic formal languages to ensure that the dataset is unleaked in large language models, because we don't know the dataset which is used in the training of these proprietary models. And by creating synthetic languages, we are assured that there is no data leakage. But the synthetic dataset that we tried, these are well motivated by models which were used in earlier classical statistical lexical translation models. So this is a minimum synthetic structured sequence to sequence task where we first generated like alphabets. So here is an example of a sequence that we generate. We generate like say sequences of length 2, which consist of capital letters. And then we have a hidden map of each letter to a number. And we put those numbers and side by side. And the goal is to check whether the model can learn this mapping from the keys to these values. This is for sequences of length 2, sequences of length 3. So we wanted to check whether models can learn such a mapping. For a human being, it's quite simple to learn this mapping. And we wanted to see whether these also powerful LLMs can also do the same. So this was the task. And what we found is that when we give these sequences to several LLMs, so these experiments here I'm showing with Llama 3. It's an open source LLM which has 8 billion parameters. But the same trend holds even for the frontier proprietary models like GPT-4 or Gemini. So what we observe is that as the sequence length is increased, the accuracy drops drastically from 100 down to 31. And then we try to sort of conjecture why does the in-context learning suffer on longer sequences? And our hypothesis is that it suffers because the LLM is incapable of learning the relationship or the alignment between the X and Y sequences. In order to validate that hypothesis, we changed the task as follows. Instead of getting a mapping from X sequence to Y sequence, in the Y sequence, we made the relationship between the X and Y explicit by interleaving the X and Y tokens based on the gold alignment that is there between these two sequences. And when we do this interleaving externally by force, then we find that the model has no problems in giving high accuracy, even if the sequence length is increased. So that led us to the question what is the capability of the transformer model, which is the core machinery behind all these large language models. So the transformer is a particular arrangement of parameters and computations. And although in theory, it's a universal function, it can implement anything. In practice, because of the way it is pre-trained and fine-tuned, it has certain biases and capabilities. And we show that independent of how it is pre-trained, we don't show, but we have an informal conjecture that a transformer with causal attention cannot in context learn input-output alignments. And because, if you look at the way these alignments were discovered in the past, they required the kind of memory which the current transformer does not provision for. And at least some kind of chain of thought or scratch memory would be required in order to implement that logic. So therefore, we gave up on trying to adapt the model via straightforward in-context learning. And then we talk about what are the options if you cannot just plain in-context learning does not work. So we discussed three alternatives. One is to just go on and do fine-tuning. But we don't just do standard fine-tuning. We do a hybrid of parameter updates and in-context learning, even during fine-tuning. And then the second two approaches do not require model updates, parameter updates, but they just change the problem so that the decompositional structure of the problem is made more explicit. And using that also, we are able to get good accuracy by not just depending on the prompts to get the model to learn a task. So in context fine-tuning, in standard fine-tuning, you give the model an input and you ask it to update the parameters so as to minimize the error on those outputs. Whereas what we do is in context fine-tuning, where to the model we give in the context examples of the task, and then we fine-tune the models. Now the model has the option to either pick up the correct answer from its context or update the parameters. And that tension, the model has to figure out what is best based on the training objective. And what we find is that as the number of training steps increase, and here you see accuracy for two different strategies. This red lines is when we do fine-tuning with examples in the context, and these blue lines are when you do fine-tuning, just plain simple fine-tuning without in-context examples. And we find that in-context fine-tuning it converges to high accuracy much sooner, like within almost 100 steps, whereas for the same kind of accuracy with standard fine-tuning, you need a lot more steps. And the other interesting finding was how the model is able to use the in-context examples to learn first the alignment between input and output sequences, and that alignment usually is learned in some middle layers of the transformer. So like here, layer 13 to 15 is where the alignment is uncovered between the input and output examples, and the induction heads, which for the test example looks up the related examples from the context, that happens in higher layers, but only after the induction heads are formed in lower layers. In contrast, when we look at the fine-tuning without in-context examples, the model, it's not clear that it ever learns to align the input and output sequences. So this is one part about how one can handle the limitation of the LLM not being inherently able to do effective in context learning when your output is not simple scalar classification kind of task. Then the remaining two methods, they are no fine-tuning based methods, but where they sort of expose the decompositional structure of the task in some other ways, which I will go over next. So this method, say suppose if you are trying to teach an LLM to take as input a natural language question of the form, schedule a team meeting tomorrow from 3 p.m. to the end of the day. And you want the LLM to convert this natural language code into an entry into a calendar. But the first step to do that is to write the program for this natural corresponding to this natural language instruction. And this program is what I'm calling as code YI. This is a Lisp kind of program. And the model, we want to teach the model to learn, say, new syntaxes of these languages with in-context examples. And just now we saw that the model inherently is not capable. So first thing what we do is we decompose the program into standalone subprograms. So this, because this program is a tree, there is a natural decomposition of the task of this tree into subtrees. So each color box here you see is a subtree of this original tree. And then to each program, then we attach a synthesized natural language query, which is obtained by taking the original natural language query and stripping off the parts which are relevant to the sub-program which has been mentioned in each box. For example, here the original question was schedule a team meeting tomorrow from 3 p.m. to the end of the day. And if you consider just this part of the tree which says create event has subject team meeting, then the natural language, this whole sentence is the part of this whole sentence which is relevant to the code here is just schedule a team meeting, and it extracts that natural language part. Now, as a result of this operation, we are able to collect examples of natural language question and programs and subprograms, and therefore we have much more granular supervision to be provided in context. And once we do that, we find that the accuracy is much higher than if we were to provide the original large trees, which can provide a lot of distraction. Then the second part, this is now a second trick. And then the third trick that we employed was to take, like say, another kind of natural language to program generation task is text to SQL generation. So let's say you have a natural language question, and corresponding to that, you want to generate an SQL program, and you have two pairs here. And now, even if you give a natural language question, which is very similar to one of the previous pairs, we found that the LLM is not able to harness them and learn well. So what we propose is a three-step fix. First, what we do is whatever label data are available to us, we make them less distracting and more abstract by removing names of constants like here TR183 is a molecule name. So we just mask it out and just call it a string. And even in the program, we change that TR183 into string. And we do that first in the program, and then we also modify the natural language question attached with that string. And after we have created these templates, when a new user question comes, we have a dedicated model to check whether a new natural language question will have the same template of code as one of the stored templates. And this model is very small and lightweight, and it can be trained with task-specific training data. And once we do that, then we find that we are able to identify the matching templates with high accuracy. But since once we find a matching template, let's call it y tilde, we can generate the SQL not purely from the LLM in a free format generation mode, but rather we use grammar constrained decoding to generate an SQL which conforms to the schema which we have externally discovered is useful. So this is the pipeline. We created this software. It is available in the public domain for anyone to use. So if you have this text to SQL generation task, where you also have a limited amount of training data, then we believe that our software could be useful for you. So with this kind of approach, here what you see is accuracy for different kind of database schema using 3 methods. Zero shot is using the LLM as is. ICL3 is just using vanilla in context learning, and this green bars is using our method, and we see significant improvement in accuracy. So this is like I've come to the end of my talk. So what we have shown is that in-context learning is very convenient for on-the-fly adaptation in multi-tenancy models like large language models. They provide decent improvement in accuracy. They are relatively robust and they are very efficient. But we need more work to understand the mechanism behind in-context learning. In-context learning can learn totally unseen tasks for scalar classification and Markov languages using induction heads, but it fails for unseen sequence-to-sequence learning tasks because input-output alignments cannot be learned in context. And a hybrid of in-context learning and fine-tuning can be harnessed to only learn the missing alignment function. When fine-tuning is not an option, we show that decomposition of large structured outputs may be useful, and template-driven representation may increase overlap. And finally, using those templates to do grammar constraint decoding can help you enforce the template at the time of generation. This is my last slide. I'll end with some open questions on ICL for few-shot adaptation. We would like to formally establish the representation capability of the transformer to in-context learn various tasks. We want to ask the question of, could additional scratch memory or chain of thought significantly enhance the capability of the LLM? And what form of pre-training can cause the emergence of ICL over structured tasks? And also to better harness long context LLMs for robust and efficient in-context learning over a large number of examples. Thank you all for listening.
Okay. Thank you so much actually for your excellent deliberation, Professor Sunita. Now it is actually open for certain questions. Professor Sanat Kumarji, would you like to now come out with your question?
Yes. Madam, I am a absolute Aam Aadmi, don't know anything about this, but you have explained something. I wanted to ask that subsequently. I will ask that question now. Actually, humorously speaking, I am trying to get human intelligence. I'm going to learn human intelligence to find out mistakes in artificial intelligence answers. So, you know, medical people use this, and then they say, if you have a cold, you do this. And somebody, if they want, is this answer right? Then somebody has to tell. I am trying to get that kind of intelligence. Anyway, that is by the side. The question I want to ask is, you in your learning sequence, you said 2 star 3 is equal to 6, 3 star
Right.
4 is equal to 12,
Right.
4 star 5 is equal to 20.
Right.
Now I have two questions. I now say find out 13 star 9. So missing numbers are there. It is not in the same sequence. I ask for some other number.
Right.
Secondly, by either as a typo.
I think that will work also, you know, because the model, what I think the model, even though I did not say star is the standard notation for multiplication, it might figure out.
I used
The
the star because
surprising
I
part-
didn't understand your pling. That's why. Pling is
Right.
pling is actually a factorial. So I
Right,
didn't.
and it still is able to figure out that particular pling, you know, it does not interpret it as factorial. It somehow identifies the pattern that this could be multiplication. Although, you know, the most surprising part is I did not even say that the first 3 characters are input and 6 is the output. There is no XY demarcation also. Everything is just an undifferentiated sequence of tuples.
No, the equal to gives the idea. No, for it. Equal to means
okay.
that equal
Right.
to you
But
put
you know,
that.
yeah, even
If you
if I
didn't put the
replace
equal to, then there will be a
with
problem.
something else, it might work.
Yeah. So anyway, in this particular example which I have given you, after 3, there is a, it is not in sequence. I am asking some other number, 13
Right.
star 9. So will
Right.
it find out that?
Yes,
it has to,
I am pretty sure it will find out.
okay, fair enough. The
Yes.
next question is that in the examples that you are giving, a person can make a typo. For example, the 3 star 4 is not equal to 12 but equal to 22, you may say, by typing at the time of
Right.
putting. Or even in nature, there is a lot of variation, there is a randomness. So
Right.
will it be able to remove the random numbers, that is wrong numbers, and then say, now this is what it is? Or it should tell the user that I say you have given the wrong in sequence. It should, one of these two, it should tell. Will it do it?
Right. So it depends on the amount of data versus the amount of data which is signal versus noise. So suppose if you give 20 examples and in those 20 examples, one of them is wrong, then it will realize that perhaps that is a typo. But if you give only 3 examples and out of that one of them is wrong, then it might be confused. It will not be able to spot the pattern.
So for it to spot the error, have you coded it? I mean, when you create the model, how do you tell that this is wrong? That's what I want to understand.
Right.
If something
So you
is
don't
wrong,
say,
it has to find out that it is wrong.
Right. So actually what you mentioned about the fact that in nature nothing is deterministic. So the examples that I said for the purposes of illustration in the talk, I put deterministic numbers, but when we evaluate, we actually, you know, say that, okay, the Y has it's sort of maybe some function of the input, plus there is some Gaussian noise. And the model is able to ignore the noise, assuming that the noise does not overwhelm the signal, and it can figure out, okay, there is a hidden pattern, and on top of that, there is some random fluctuation.
Okay.
It can figure it out.
Okay. Last is that in the last question, in that sequence, is there a minimum number of examples you have to give, or just one example will do, or any number of examples?
Actually, that also is a very good question. Yeah. So, you know, sometimes it learns even with just one example, but then it should kind of know the task already. So right now, like for text to SQL, you know, the model already knows about text to SQL, but maybe a particular database, like the model knows how to use, say, university databases or standard industry databases, but then you want to apply it on some pharma database, which it may not have seen, say. So then just one example might orient it, you know, it's sort of, that is why there is this second hypothesis that I did not go into, where the model uses the in context example to just recognize the task as a human would. Make sense?
Your last sentence has got chopped off because the audio was not okay. Can you please repeat
Okay.
your
No, I said that the model, like the way a human, sometimes if you just give one example, then the human is able to recall the previous learning based on just that one example. So using that one example, it's not learning the task afresh. It just uses that one example to recall from memory previous experiences where the user may have learned that task. And a similar thing perhaps happens in an LLM.
Okay. Thank you. Thank you, madam.
Yeah.
Anybody else?
Yeah, Professor Acharya, just
please.
Just a follow-up question. Very nice talk. Ma'am, you addressed randomness there, but if there are inherent biases in your input data, how do you handle that?
Can you please provide an example of the kind of biases?
Let's say we have strings there which is sometimes termed as sexist. For example, I want to eliminate that. Chairman versus chairperson and all those kinds of language issues.
Right. Yeah. So, these days, the LLM is surprisingly good at following instructions. So if you explicitly ask it not to incorporate any gender bias, so this is independent of my talk. I'm just talking in general about LLMs, right? So, and particularly such issues which are very international, it might be able to, it is able to, at least for the head cases, like for 80% of the cases, it is able to produce output which is safe. The model will produce output which is safe. But whether, there is a lot of debate on what is even the definition of bias.
Yeah, say from a population vector, I'm subtracting, and say all are doctors. I'm subtracting the male part. It doesn't give me female, it gives a nurse, something like that. Male, something like that.
Right. Yeah, but see, so the main tension is this, that the whole of machine learning is about learning based on prominent patterns in the data. So why should we ask the model to have a different notion of bias and morality than what is present in the data? So one should actually go to the source, right? I mean, the model is just a mirror to the world.
Yeah. Yes. So in this machine learning, huge number of weights you talked about, are those weights the values you take all are randomized, or?
Initially, they start with random values, and then once you they start with that, but then after you do the pre-training and then the supervised fine-tuning and then the reinforcement learning based fine-tuning, then they are very far from random.
Very good, very nice. Thank you. Thank you.
Welcome.
Patil sir, would you like to ask some question? Yes, please. Now we can say. Hello, you are not audible.
No, he's not speaking. I think Dr. Pradeep wants to say something.
Okay. Dr. Pradeep,
Hello.
please.
Yeah. So I am not an expert in this. You can hear me?
Yes, I
Yes,
can.
we can hear you. Please.
Yeah. So I am not an expert in this, but I just listening to you, it dawned on me that DeepSeek was doing exactly same thing or what? Because they are saying DeepSeek use the data of Anthropic this thing, and then they came up with their own models, which are much more, I mean, much cheaper to run. Is something like that they are doing?
No, that is very different. I mean, what
I
I
see.
was talking about is in context learning.
Huh.
I don't know how they obtained their data, but they were doing standard fine tuning.
I see. But I'm sure you know what DeepSeek is being accused of, like how they have managed to steal data and all that stuff.
Well, so the whole of AI, if you think about it, there are, artists and content creators who are very upset that their content has been, I don't know whether you would call it stolen or not, but they have been used to train these large language models. And now people who use this public data to train these large language models, they are taking away the revenue and the mind share. Earlier, at least in the internet era, if somebody produced a very useful web page, then that original web page would be there, and if the world would be able to know who was the creator of that content. But now if an AI model is sucking away all the content which has been created, distributed in a distributed fashion from millions of people all over the world, and now it's sort of distilled and summarized in this giant model without any attribution, so it's all, it's very difficult to blame any one party.
Okay. Thank you.
Madam Sharma, would you like to ask something?
Yes. So the lecture was self-explanatory. It is well understood, so I don't have any questions. Audible, sir?
Yes,
Some,
yeah, I heard you. Yeah, yes.
Okay. So, sir, can I proceed with the vote of thanks, sir?
Hello?
Sir, can I proceed with the vote of thanks?
No. I would like to actually ask one or two small things, may not be connected with your LLM and all these things. First of all, now actually something like speech to text is very well known for all languages, many languages. But let us say a language that is Santali.
Mhm.
It is actually spoken not only in Odisha, Jharkhand, Chhattisgarh, Bihar, Assam, including Nepal. But it has got actually no, very little actually written things. It is all spoken. And most likely this will be included in the 8th schedule very soon, because there is a lot of demand in that. Okay. So how actually this could be done? Because this is very important.
Right. So actually, at a national level, there are efforts like Bhashini, and then there is Project Karya. Lot of efforts to collect data for these languages. I know that Google is doing it, and at the Government of India level, there is a Bhashini project. So there are lots of sort of these apps kind of ways by which, the people speak, and then those are transcribed. And of course, there is a chicken and egg problem. First, you need to have a good Santhali model in order to even get AI to do the transcription properly. So initially, you need a little bit of bootstrapping data. And so there are multifaceted approaches of handling the introduction of new languages into a multilingual model. So one discovery people have had for multiple years now, almost 10 years, that even if you have a new language, instead of starting from scratch, if you start from a model which has already seen, let's say, 20 languages, it requires lesser data to introduce a 21st language. I mean, that makes a lot of sense. And particularly among Indian languages, there is enough overlap and relatedness among languages. So with that, but even so, even if there is relatedness, you need a little bit of data, and that has to be done manually. And there are already like efforts both from companies like Google and at a national level to collect data. And so I think at least languages like Santhali, now it has come to on the radar of many people who are creating Indic
Yes.
language models. And I think
is true.
that will be sort of addressed quite well in terms of AI's handling of Santhali language.
Now, even Odia also suffers from that type of thing. If not many things are available.
Right,
Okay.
Odia also. Right, exactly. So although less so than Santhali, at least for Odia, there is a lot more
Yes.
even Wikipedia, there are a lot of Wikipedia pages on Odia, which is not there for Santhali. To the best of my knowledge, I have not looked for Santhali Wikipedia pages.
Anyway, another personal note I'd like to
Yes.
share with you. I find actually these two Malu brothers, they are your collaborators.
Right.
Okay. They happen to be, grandson of my student, Rajanikant Malu.
Oh, that's very interesting to know. Okay.
And actually, both of them came along with Rajanikant to ask me that which institute they should join. I said that, okay, you join IIT Bombay. They said that we will not get computer science, both of us want to read, but one will get computer science, another will not get. I said that definitely you can try and you can do this thing, not much of problem. And I'm so happy that they are actually collaborating with you. Okay.
Yes, yeah, good to know.
Please,
Yeah.
please convey my best wishes to them.
Yes, I will do
Okay.
that. I'll do so. Okay.
Now, anybody else? I find actually Oro Srivastava. Would you like to ask some question?
Thank you, sir. Thank you so much. But unfortunately, due to some work, I was
Please.
away for some time.
Hello, is not audible.
No, I heard what he said. He said that because of some work, he was away for some time, and it does not look like he has any questions.
Yeah,
That's okay. Yeah.
So I'm sorry for that.
No
but
worries. No
still-
worries.
May I now request Madam Renu Sama to please propose a vote of thanks. If you have got any question also, you can ask.
Thank you, sir. Honorable Chairman, INA Bhubaneswar Chapter, Professor Damodar Acharya, sir. Distinguished Speaker, Professor Sunita Saragi, esteemed fellow, INA, esteemed fellow, esteemed senior member, IEEE, respected faculty and scholars. A very good evening to one and all. It is my proud privilege to represent the vote of thanks for today's 25th distinguished lecture organized by INA jointly with Sikkim Sundam to be University, CSR, IMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, ICT IOC Bhubaneswar campus, and IEEE Bhubaneswar section. Deeply honored to have you, ma'am, for this particular distinguished lecture. You lecture on beam prompting, structure about adaptation for reliable elements has provided profound insights aimed at advancing faculty and structure-aware intelligence in large language models. On behalf of all organizing institutes, I extend our heartfelt gratitude to you, ma'am, for sharing your valuable knowledge and research perspective. I also sincerely thank the leadership of all partner institutes and participants and their enthusiasm and active engagement. Thank you all for making this lecture a grand success. Jai Hind. Namaste.
Okay, thank you very much.
Okay.
Yeah.
Thank you very much.
Thank you.
Yeah, okay, bye.
I'm so happy.
Yeah.
Thank you. Thank you.
Thank you so much, sir. Thank you.